So, welcome to week 6 of our Engineering Basics workshop. Um, we are going to continue talking about stress and strain today. Um, so, last time we kind of finished up talking about strain. We did an example in double shear. Um, this week we're going to kind of fully flesh out the idea of cut free body diagrams, and we're going to talk about axial the basics of axial members. So stress and strain in one dimension. All right. So just to review again, because this is always something that's confusing that I think needs review. Josh, can you give me a good definition of what is stress?
Would you like me to think of it off the top of my head or read it out of my notes?
Um, I want you to give me a non-mathematical definition.
Um, I remember stress was like the amount of force you put on something, and then strain was how much it alters from its original position.
Okay. And just besides the amount of force on something, what else? What else do we
Specifically
care about with
pressure.
stress? Say that again.
As in pressure, as in force over area. So it's stress is usually measured by pressure.
No. So stress
Or
is,
no.
remember, yeah. So remember stress and pressure, although they have the same units, they're different things. So a pressure is a force acting on the outside of a body. Um,
Mm-hmm.
Technically, if you're talking about a fluid, it's the force acting between the molecules within the fluid. So between the particles or between the bodies. Stress is the force acting within the body. So in a fluid, you kind of talk about shear stresses, which you consider your bodies are layers of fluid, and that's kind of analogous with rigid bodies, or non-rigid um, with material bodies. So we want to think of stresses as the force per unit area within a body within a body. So the force that the body puts on itself in a given area. Okay? So that follows. What is strain? It sounded like you had a good idea of it, but let's try again. A non-mathematical definition of strain.
Um, how much the object is like warping, kind of.
Warping. Okay, that's a good way to think about it. Um, and then how would you say strain is different from displacement? Because they kind of both talk about warping, but what's the big difference there?
Oh, isn't strain like in multi-directional? Is it like
Well,
it
you could have displacements in multiple directions, right? I can draw a coordinate system and say I'm displaced in multiple directions. I'll
I
give you a
think
hint. Strain doesn't have units, right? It's a fraction.
oh
Is
yeah.
it a fraction or a percentage? So what does that mean?
Um it's like a proportion of what it was before.
Yeah, so we would call it like mathematically, you would call this normalized. We would
Mm-hmm.
call this normalized.
Mm-hmm.
Normalized. Which just
Um
means that if I have a bridge, if I have a bridge that's a mile across and it displaces a foot, that's about the same thing as something that's 500 or that's I don't know, maybe that's a big bridge. Let's say it's 100 feet across and it displaces a foot. That's the same thing, the same amount of strain as a pole that's 10 inches long, or sorry, 100 inches long and gets displaced 1 inch. Right? So your fraction, your ratio is what we care about here. Because obviously in a bridge, there's a lot more material that has a chance to move. If we were to displace this 100-inch, if we were to displace this 100-inch bar a whole foot, that would mean we'd stretch it this much. Whereas, with our 100-foot bridge, displacing it a foot isn't nearly as dramatic of a displacement there.
Sorry to stop you again, but do you mind restating what you said about stress just a few minutes ago? I got a notification that popped up about like some purchase that I didn't make. So
no problem.
Hear that.
So remember, stress we think of as the force per unit area, because the idea here per unit area is that we want to use stress to be as descriptive as possible in lots of situations. So stress and strain, the reason that we divide by area or that we divide by the other length is so that we can compare things that are of different size scales. So back to our bridge example. I have a bridge that is in compression, right? Let's just say we have some support here, and we're gonna put some supports there. We'll put a force like this on our bridge. So it's gonna put the bottom here in tension. It's gonna put the bottom of the bridge in tension, so it's gonna try and pull it apart. It's gonna push the top together. Now, we have concrete and like reinforced steel beams in this bridge. And even though these things are massive, they have cross sections that are huge. You could have a whole car, right, inside the box of this bridge, or for modern bridges, several lanes of cars. We can still talk about it as experiencing some amount of stress. And that amount of stress is the same as something that's much smaller. So just in our bend tester, we have an instron, we put a couple pounds on here, but the situation looks the same. So stress is just talking about the actual force that we're putting onto it spread out over the area. So in our instron test, this one down here, that might only be a couple pounds. In our bridge example here, that'll be a couple tons. But we can use steel in both of these. We just have a whole lot more steel here than we do here. So it's the force sort of normalized to the area because we know how this material specifically will react. We know the amount of stress that these materials can handle for a given amount of material. And then the last part here is that this all happens within the body itself. So these are forces that are trying to either pull the body apart or push the body together. Stresses, the reason stresses are different than pressures are something that we think of as moving the body. We think of them as acting on rigid bodies. We think of them as acting all over the place, so in multiple places. This might be a pressure distribution, but they all act to move the body rather than to like squish it. And stresses are what we talk about within the body that's actually changing how it's shaped. Then similarly for strain, it's the same idea. With strain, you're talking about this body is being compressed or stretched. We're talking about the body actually changing shape rather than the body moving. One thing that I know we talked about a while ago, but I know it's been a couple weeks. One thing that we assume for the model that we're using, for the isotropic linear elastic model. Did I spell that right? Isotropic. Oh, that should be an M, not an A. isotropic linear elastic model is that these are all comparatively small deformations. So in the case of my mystery beam here, we're talking less than 2%. Less than 2% change. And usually it's less than 1%. The reason that we do that we use this model, is in engineering, like in C204, a lot of times we're talking about bridges and stuff. So if your bridge has a displacement greater than 2%, then it's probably going to be breaking. And you don't want to design anywhere around that. And this model describes the physics, describes the material properties pretty well within that small range. As mechanical engineers, there are times where we actually see larger displacements than that. There's a whole field of engineering. What's it called? The word was just on the tip of my tongue. But the whole idea is you design things that are allowed to sort of strain more. One easy thing to think about here is like plastic lids. So a lot of times plastic lids have this really thin section at the end, where you can use it as a hinge, right? And it's still one thing. It's actually still decently described by this isotropic linear elastic model. But in general, the assumptions that we make are not for this scenario. So they're not for something like this. We're trying to make solid structures, we're trying to make rigid things, and we're trying to keep them rigid. Or we're trying to model them to displace only a small amount. Make sense? All right.
Yes, it does. Sorry, I was hitting the wrong mute button.
That's fine. Okay. So if we think back to last week, we had these definitions for stress and strain. So we have sort of three different equations here. So this first one here just comes from our definition. Remember, P here is just another variable name for force. So this is our definition equation, force divided by area. Then we have this equation here that comes from Hooke's law. So this big E here is Young's modulus. Young's modulus. This one is strain. And then we have stress over here. And remember, we basically said, okay, we can picture this big steel beam as basically just a really stiff spring. So if we compress it, we expect to see a force that's proportional to the amount that we compressed. So this is about akin to Hooke's law. So F equals K delta X. And then lastly, here we have the definition of strain. So we have a little change in length. So if we were to have strained this thing, we call this the delta. So this is delta L, the change in length, over the original length. Over the original length. So we can use these definitions to combine them into one to make it easy for us to predict for a certain geometry. So I have my unknown geometry here, or my known geometry, or the geometry I'm trying to design with a given force, the given force in known geometry. So we know the length, and we know the cross-sectional area here, right? So this is I'm just going to assume it's something like that, about a triangle, circle. Sure, we'll call this a triangle cross-sectional area. So we know A, we know L, we know our geometry, we know the force on it, and we know what material it is. So we know this Young's modulus, this material property. So we said before, if we just solve this equation for this equation, we get U, our displacement. I'll call our displacement here U. This is U. Displacement equals PL over EA. Now, one interesting thing that you'll probably see with what I drew here is we actually have two different areas. So we have this larger section. We also have the smaller section here. So we could have two different areas. What I'm about to show, which is kind of a better explanation than we've been giving of cut free body diagrams, is that this displacement is actually the sum. So if we grab our eraser here, to generalize this a little more, we want to say this is the sum of all of these for the different geometries, different materials, and potentially different forces. So here we have one force. So U equals the sum here. We have one force, but we have two areas. Now, this I'm assuming is the same material, so E happens to be a constant, but it could be two different materials. You know, I could have this part that's steel. This part could be, we'll make it iron. Iron, this could be Fe, and this part could be copper. Cu could be copper. Now, iron and copper each have their own Young's modulus. They each have their own material properties. So we would rewrite this. We could regeneralize this, or for this, not general, but for this little specific thing, we could say this is P times LFE. We'll call this length here LFE, L of the iron portion, over E iron, so EFE, times the area of the iron portion, AFE, plus the same thing, so it's still the same force acting on it, but now we have everything for the copper. So P times the length of the copper, so this portion here is LCU divided by the material properties of the copper, so ECU, ACU. And I mean, if you think about that, it kind of makes sense, right? If I know that PL over EA, so PL over EA, if I know that's the displacement of one section, then if I have a whole bunch of sections chained together, well, it makes sense that you just take the sum of all of the little sections. Sometimes you'll see this expressed as an integral, so it'll be U equals the integral of PL over EA. And usually if you write this as an integral, they actually integrate over some dimension. So a lot of times you see this PL or P dx over EA from 0 to length L. So they're just saying this, we're going to sum up all of the little displacements along X over our length from 0 to L. This is something that becomes a little more useful when you have weird shapes. So if rather than a constant cross section, you have something like maybe something that's tapered, then that integral definition becomes a little more useful. Because now you can just talk about your area as a function of X, as a function of length here. It's math. There are 100 different ways you can describe this equation that might work better in different scenarios, but ultimately this is really what we want to end up with, that U is just the sum of all of these forces divided by areas times the length divided by whatever that spring constant is, that Young's modulus here. So, following that, I want to do an example problem. So, we have been provided by our favorite C204 professor with this fantastic little example problem. So I have stated that the material that we're going to design this rod, the material that we're going to design it with is carbon steel. So I just chose the material properties of carbon steel that is provided in Shigley's. Typically, if you were to actually design something, you want to design it with whatever material you're purchasing. So most material manufacturers will rate their material to a specific grade or a specific standard. So, for example, if you have aluminum, one of the most common types of aluminum is 6061-T6. This is basically just says it's this alloy, 6061 alloy, and it's been heat treated to this specification, and that has some strength. So it just has some material properties. It's got some E, some tensile strength, some Young's modulus, some Poisson's ratio that is generally known. If you have some more exotic materials or manufacturers that are trying to get an edge, then they'll provide you specifically with their test results. So sometimes you'll say, and this isn't as common anymore because a lot of materials, especially the common materials that we build with, there's a very wide market. But not that long ago, even 100 years ago, some foundry in some part of the world might have some special formula for their steel that happens to be a lot stronger. So they'd have some percentage of iron, some percentage of carbon, and then they probably have other things in it like magnesium, and some trace elements that either help with alloying or can change the stiffness, change the if it's something like stainless steel, you can change its corrosion resistance. But these are all things that you should be able to get from a manufacturer and collect your material properties. So we know E. We are using the good old Shigley's foundry, and we're going to machine this from their stuff. So with that extremely long lead-in, now we know we need to figure out how we're going to design this. We want to figure out how much is our rod that we've designed going to displace with a force of 29 kilonewtons. I don't know, let's say I'm trying to pump up a car. Let's say this is part of a bottle jack, right? I'm trying to support a car's weight with this. So we're gonna put a bunch of force on it. And with these dimensions, I don't know if that could hold up a car, but we'll see. We'll have to figure it out. So we need to sort of split this into multiple sections because right now we just have this one equation, U equals PL over EA. And we need to really formally split that up over our whole body so that when we're showing our employer or if we're showing the government something, then we want it to be approved for safety reasons. We want to be able to sell this to car manufacturers, and we want them to be comfortable with letting people use this. We want a good way to describe this. So if I take my body here, let's go ahead and add a new page. Take my body, and I'm just going to start drawing a free body diagram on here, and we'll kind of go along as we do. So I have my applied force P. It's applied force P. Stretching it. I know that this section over here is rigid or is fixed. So I know that this can resist a force against it. because this is a free body diagram, first thing I want to do after kind of drawing my scenario, I want to put axes on here. So oh, that wasn't straight. This is our, what the middle one? Call this our x-axis. We'll call this one y-axis. And then what isn't shown here, or what I'll kind of draw obliquely here, is our z-axis. We've got x, y, and z. And again, for simplicity's sake, I'm going to say this thing is circular. A lot of examples that you see are circular. The reason that we do this is just because a circle is really easy to calculate the area, right? You just need r. As we are lucky enough that we know that the area of a circle is pi r squared. Which, if you look back here, actually are the dimensions that we're given. So we're given radii for each of these sections, and we're given a length overall. I'm assuming this is evenly divided, so each of these is whatever 84 divided by 3 is. 28? Yeah, 28. All right, so we have our body. Now, we now have a coordinate system. We just need to draw our reactions. So we have one force in the x direction, none in the y, none in the z. So we know it doesn't have to resist either of those to be considered static, because at the end of the day, this is still a statics problem. This thing isn't moving. So we know that we need one reaction in the other direction to even things out. Because we have a wall here, we have a fixed position, we know that this can provide that reaction. So I'm going to call this R. And a quick solution to our statics equations here would show that f of x equals 0. So we've got positive p minus r equals 0. P equals r equals 27 kilonewtons. Is that what I said? 29 kilonewtons. Okay, so now we have an overall free body diagram. But I only know discretely for each of these sections what the areas are. So if I'm going to divide the stresses up, we would expect to see a lot more stress in that smaller zone, right? If we were looking right here, we would expect the stress to be a lot higher and the strain to be a lot higher than we would in something larger. Just think about slicing up, I don't know, slicing up some carrots. If you have baby carrots are really easy to slice through, but a log is very big and much harder to slice through. That's because the log has a lot more material, a lot more area that you have to put a force on, loosely. Obviously, there are some different properties at play there. So I want to, we call this resolving. I want to resolve this into the stresses that can be analyzed for each section here. So I am going to cut my body here. Just cut it right there. Doesn't matter where, but I want to cut it right here, right on this section, just because this is a convenient landmark for me, sort of right on the border here. And I want to look at this side. So I want to look at the small area here. So if I were to draw another free body diagram, we've got this section here. Let's see, I'll outline in red here what we're cutting. So we're going to draw another free body diagram just of this portion. So for this free body diagram, we've got the cut section here, our cut line right there, and we still said what our reaction is. So we still know that the body experiences a force here. So our coordinate system, I'm going to leave the same. So we've still got x and y, and then z in the oblique direction. But now I have there has to be something happening here that resists this r. Now this is where you start to kind of see the differences and similarities between a force and a pressure. So, or sorry, between a stress and a pressure. So we know that the stress here is equal to a force divided by an area. So I'm going to just loosely say, just for example, or for the sake of argument, I'm just going to say I have some interior force here, Fi. That kind of got fat. Let me make it more legible. Fi. I have some internal force here that's reacting to this. And I know that I have an area here that this material is letting me apply that internal force over. You probably think, okay, I've got some internal force applied over some internal area. That is a stress. So I can say my reaction here, let's draw this again. Draw this again here. I can say that this reaction is the same thing. Oh man, my straight lines are becoming less straight. This reaction is reacting to a stress pulling in this direction, acting over the whole area. Right? So we'll say this is our stress. So if we take this further, now we know the stress applied on this face. And we can calculate a small displacement when we know a stress. So just for this section, just for section 1, we know the internal stress, we know E, we know A, and we know the length. So that's all we need. We say U equals PL over EA over EA. This P over A here is our reaction stress, right? That would be this reaction force. It is the same thing here as P. This area, which we were given earlier, well, not given, but we're given the radius of it earlier. We can calculate. So here, oh, I think I jumped ahead a step. We know R, and we know that there is a stress here. Whenever you cut something in a free body diagram, that is a stress. We can calculate what the stress is by resolving the forces. So in free body diagram number 2, if I do the sum of the forces in the x direction equals 0, I can say R equals, minus R plus Fi equals 0. So Fi equals R equals P. And I know that this is a valid assumption because where I split this free body diagram, where I made my cut, I know there has to be some stress there, which resolves here. That resolves there. So for section 1, we'll say U1 equals this R, which is P, which is F1, which we already know is 29 kilonewtons, times the length, which is 84 millimeters over 3, divided by E, which was, I think, 207, yeah, 207 GPA times the cross-sectional area times pi r, which is 10 millimeters squared. Which, let me plug that into a calculator here, 29E3 times 84/3 divided by 207 times 10 to the 9th, because remember that's giga, that's 10 to the 9th, times pi r squared, O squared. Oh, and I need to divide by 1,000 one more time, because I had a millimeters in there. Should be, and if you want to check this, go ahead. I could be wrong here, but it looks like it's 1.24 times 10 to the minus 5 meters, which is the same thing as multiplied by 1,000. That's 0.01 millimeters, which is great. That means that the smallest section of our jack here only displaces 0.01 millimeters. So that's fantastic. That means that the next sections that we have here are going to be better. So let's do section 2. So for section 2, if we draw this out again.
Can we go back and look at your math real quick?
Yeah, I could easily have gotten some decimals off there.
Oh, that's fine. I'm just trying to look at units here. So you started with kilonewtons on the top.
Yeah, so kilonewtons here.
Yeah.
Force is given in kilonewtons.
What is that G for?
G is giga, so this is gigapascals.
Oh, gigapascals.
Yeah, so that's 207 times 10 to the 9th.
I was wondering why I got such a huge displacement.
Pascals. Yeah.
I was like, man, my displacement's like in the high meter values.
Yeah. Let's see. 28 was I right there? 84/3 should be 28. Yeah. So this thing's 28 millimeters long, about a foot. If you're stretching something about a foot long, you wouldn't expect it. You'd expect it to break after you stretch it more than a millimeter or two, right?
Yeah.
If it's carbon steel,
Mm-hmm.
Maybe a little farther, but this is also half a foot wide. So if you had a pipe that you were trying to stretch longer than that, then you would expect to see some pretty high, or you would expect to see some really small displacements here. So now onto our smaller section, or onto section 2. For section 2, now we've already made one cut here. And we solved. So we had R, we have P. We already solved.
How many is again?
Sorry, repeat your question.
How many is giga again?
Giga, so giga is 10 to the 9th.
Oh.
So you have kilo is
okay.
1,000, so that's 10 cubed. Mega is a million.
Million gigas.
10 to the 6th. Giga is 10 to the 9th, or a billion. So if you have a flash drive that's 32 gigabytes, that's 32 billion bytes. Or what is that? 32 times 8. So it's 256 billion bits. Okay, so back into mechanics land. So we've made our cut here. So we already solved this section of our free body diagram. So we already solved this portion. We figured out what this force is. So we now have R and Fi 1. We can do exactly the same thing and just make another cut here. So we make another cut here. We know that this cut, because it's applied over an area, we have to have some stresses here. The body has to be reacting because we are inside of the body. So we only see stresses on the inside of the body, no forces, just stresses. So we've got a new cut there. We know R is still the same. R here is still the same. And we know that we have to see some stresses coming out here, or some stress. So this is sigma, we'll call it sigma of section 2. So we can also write sigma of section 2 as a force over an area. So we can say this is equivalent to some internal force 2 acting here, and then we can do statics on it. So our sum of forces in X equals 0, R minus R plus F internal number 2 equals 0. So remember, we just multiplied by the area here to get this force. And if you're not comfortable with that, you can even just keep this as a stress. So we said U equals PL over EA. Well, you can say U equals stress times L over E. And we know here R, or minus R, plus sigma 2 equals 0. Because sigma 2 is applied over an area, and we're just talking about forces here, we say sigma 2 times our area. So sigma 2, sigma 2 times our area equals 0. And those are one and the same. Yeah. That goes there. Yep. See, and these are
sorry. Is sigma 2 different than the first sigma that we used in the first problem?
So the areas are different. So
okay.
If you look here, let's say, in fact, there's a good explanation. That's a great question. So let's say for this diagram, instead of making one cut, we make two cuts. So we've got some other cut here. So we have some stress pulling on the body this way here. So from this side, pulls this way. From that side, it pulls that way. I'm just going to copy all of this. Copy and paste it. Oh, that's not what I wanted to do. It pastes them each individually. That's funny. If I paste that, move it down here. Those are the same thing. So we cut them in the same, we cut these, like this is the same cut. This is the same cross-sectional area here. Like I could draw, in fact, I will draw our cut line there. This area, if you were to imagine these things like being linked together, right? You'd have to pull. So if we have this as a chain link, you'd have to pull on one side. You have to pull on one side, and this side has to pull back. So this is where we see an application of Newton's laws. We have an action here, an action that's, it's being pulled. This is what we're actually doing to it, and then a reaction there. So we can draw this stress as an action here along the cut and a reaction here along the cut on the other side. The reason that's valid, right? These things mathematically are equal and opposite, so they cancel out. So if we cancel this all out, if we just completely remove that from the picture, then it's like we never cut it at all. So we could then move all this, just move it right back over, and now it's the same thing as if we only made one cut. So, since we know we can use cuts appropriately like that, now if I know, I said we last time we calculated what the stress was here. The stress here and here have to be different because the areas are different, and there isn't any other force. So we have the same force P. This same force is being applied throughout the whole body. Everything in here experiences this force, but they all have different areas. So what we keep seeing, right? We keep seeing one reaction, one internal force, or one applied force and one reaction. So there's only one force here in question. We're always going to, our sum of forces here, our statics equation, is always going to just give us one internal force and one value for it, which is 29 kilonewtons. But our areas are changing, so our stresses, our internal stresses, must be changing. For this section, the internal stress, or the stress that we see here, is 29 kilonewtons divided by pi times 0.01 squared, which is some number. You can do the math. Here, what did I say the middle one is? So this is 18 millimeters. So in the second section, now instead of 0.01, this is 0.018 because it's 18 millimeter radius. So as our internal area increases, our stress decreases, right? As this area goes up, the internal stress is going to go down. Because, well, not because, but the force that's going throughout this body that everything has to react to always stays the same, right? If you think back to like physics 1, if you have a cable, if you have a rope that you're pulling in tension, we say that the tension here in the rope is the same as the tension here. Your tension force applies throughout the whole body. Here, it's exactly the same idea. We're just saying that we have a different area over which that same force is being applied. So we see our different stresses come out here. I'm going to erase some of this to give some space back. So for the second section, we have a stress here and a stress here. So we can say sigma, let's see, got sigma 1, that was this one, sigma 1, and it's now a reaction because we're on the other side of our cut, minus sigma 1 times area 1 plus sigma 2 times area 2 equals 0. That comes from our statics equilibrium equation here. This is exactly the same thing as our internal force, Fi1. And this is exactly the same thing as our internal force here, Fi2. Fi2, Fi1. We're just reducing it to make our math easier. Equals 0, fi1 equals fi2. Okay, so let's go ahead and make one more new one here. Ooh.
So, quick question.
Yeah. Yeah, go ahead.
So, if area is the only thing that's varying, can we actually factor out all of the constant values and only have the summation of the area and multiply it as one big function to
You
find the
could.
total?
Yeah, you totally could. So, in fact, yeah, when you do this by hand, there's no way you ever want to handle all these little variables, right? It's tedious, it's
Okay.
annoying. So we know,
Mhm.
yeah, we know that E is constant for everything. We know P is constant for everything. We know that all of these little sections, we said before that they're all the same length. So we know L is constant for everything. So really, this just becomes P L over E, and technically this is L over 3, right? Because each of our areas is different, times, or sorry, this should be divided by area 1 plus area 2, sorry, that plus, here, we'll call this some constant. So U equals this, all of our constant terms, times 1 over area 1 plus 1 over area 2 plus 1 over area 3.
Mhm.
So yeah,
And
you can totally pull all these out.
for length
So
over 3, does that...
oh, I'm just calling this L. So this is L over 3.
Okay.
I'm just calling the total length. The total length here is L. This is the 84 millimeters. 84 millimeters equals L. And each
Mhm.
of our subsections is L over 3.
And then wouldn't that be L in that part of the equation? Because when you take it into the summation part, say each part was L over 3, if you're adding L over 3 plus L over 3 over plus L over 3, isn't that the same thing as adding, or isn't it the same thing as 3 times L over 3? Because it's on top of each one. Maybe.
Maybe. Let's work it out. Let's see. So if we expand this, we have P L over 3 over E A1 plus P L over 3 over E A2 plus P L over 3 over E A3. The issue here is now your denominators are different. So you can't just have this as L. If this were your whole length, even though your whole length is the same, you have to remember the sections that we're talking about. We're summing up all of the little displacements in each section. We're not summing up when we do this, when we say U equals PL over EA, when we discretize this, we're talking about this just for the one section where we've made some cuts. So this is just the displacement UN, right? This is just the displacement for that section that we made the cuts for. We want to
Yeah.
sum up everything. Yeah, we want to sum up all of the displacements over our whole length. But if you have the whole length here, so if instead we make this L, if instead this is L, then now we've said that we're displacing each of these things. We're saying that this displacement applies over the whole length. So we're now basically saying that we've got something that looks like this plus something that looks like this plus something that looks like this. And all of these extra areas start to stack on top of each other.
Yeah, that makes sense.
Mhm.
Yeah, and I kind of realized too that with that logic that I was using, if you were to factor out, the pressure, it would be 3p and not pressure, because I was thinking that you needed to add them, but I quickly realized that that is not the case.
You definitely understand, but I just want to make sure this is not a
Yeah.
pressure.
Oh, yes. Yes. Sorry.
Pressure. This is not a pressure. This is just
Stress.
another name for a force. Another name for a force. We just
Yeah.
call it P because that's what the variable gods decided. We could call it
Yeah.
N. Doesn't matter. We can call it whatever letter we want, but at the end of the day,
Hmm.
this is still a force, not an area. Okay,
Yes. Okay.
so we're getting to the end here. We now have now that we kind of know that we can cut this into multiple pieces, we can add everything up for each section. Let's go ahead and solve our problem thoroughly. So I like your approach. We'll say U equals P times L over 3 over E times 1 over A1 plus 1 over A2 plus 1 over A3. Interestingly, this also works the other way around. So if you have some missing area here, let's say there's a hole in this, well, you can just subtract out the area that's missing. So let's say this is A4, right?
Hmm.
Where's my eraser? If I wanted to, I could just subtract out, there we go. I could just say minus 1 over A4. You could think of this as like a negative area if you wanted. Some area that we're no longer talking about putting a stress on.
But of course, that one would also be dependent on a different length.
Yeah. So in this case, you're correct. We'd have to actually pull this one out of the parentheses and talk about L4. You'd have to have P L4 over EA. Yeah. That is totally something that you can do and something that makes your job a lot easier. Um, let's actually run the numbers here. So U equals 28K times 0.028. That's 84 millimeters divided by 3 over 207 times 10 to the ninth. Multiply that by 1 over pi times 0.01 squared plus 1 over pi times 0.18 squared plus 1 over pi times 0.018 squared. This is times 0.022 squared because we're in millimeters here. I think throughout C204, 207, and honestly even design 1 and design 2, one of the most common errors you run into is you either forget a 0 there or you forget these pi's and you say 1 over 10 plus 1 over 18. No, it's not. It's actually squared. But if we solve that, we take the liberty to plug that into a handy dandy calculator. Do you want me to do it or do you want to do it?
Oh, I got it. I already plugged it in.
Perfect.
So I calculated my force as just newtons, like I converted it to newtons, and I didn't leave it in terms of kilonewtons.
Mm-hmm.
But I got 1.89, 1.89199999 times 10 to the negative fifth.
For the stress?
For you.
For you, for the displacement. Okay, cool.
Yes.
I get 1.583 times 10 to the minus fifth meters.
Okay.
And yeah, some of the decimal stuff in here is just about what did you simplify pi to? Where did stuff come out? That kind of thing.
What did you plug in as your pressure? I mean, not pressure, force.
Should be 29. Oh, haha! I did 28. Should be 29. Keep writing 28. 29.
I looked at it. I was like,
there we go. Yeah, that's what it is. Should be 1.639. I get 1.639. Is that what you got?
No, I got 1.89. So still a little bit different, but
either way.
Yeah.
Either way, still a really small number.
Yeah.
Yeah, and I'm sure you can do math, and I'm sure. Well, I'm not sure I can do math, but I'm sure you understand the concept.
Yes.
Which is fantastic because that is all we have time for today. But that is fine because now we can do axial members and we can do cut free body diagrams. We can do those, and we can do those. So we can do anything of any shape. Doesn't matter what shape it is. It can have some missing area. That's fine with one force. Woo!
That'd be quite difficult to calculate.
Yeah, that would be a weird one. The real trick here is you get SolidWorks to tell you what all these little bits are, or whatever your modeling thing is. You get it to tell you what the area is, and then it tells you whatever your stupid integral area equation is. Then you multiply that by all your constants.
Got it. That makes sense.
Over E. And one of the reasons, again, why you like to pull L out and make it a differential is because then you don't have to, then you can leave these other things as constants, and this is a really tiny, and it becomes a fairly simple equation.
Mm-hmm.
I think one that he sometimes likes to throw at you is he'll do something that's like a parabolic shape.
Mm-hmm.
So you actually have to use some calculus to say what the area is at each section.
Mm-hmm.
But yeah, that's all I'm going to cover today. Next week we'll finish up our topic with a full definition of this model that we've been working with and learning about. And then we can start talking about, after that, we can start doing more complex things. We can talk about trusses and frames. We can talk about stuff in shear rather than just stuff that's being pulled or pushed in one direction.